people who are in the waiting room. Okay.
Thank you. Yeah.
So welcome everybody. Today's seminar is about turbulence near absolute zero. The speaker of today is Carlo Barenghi, and I take a few minutes to present him, to introduce him, and then I leave him the stage. So Carlo Barenghi graduated in theoretical physics at the University of Milan and did his PhD at the University of Oregon in USA with Russ J. Donnelly. And then he moved to Birmingham in the UK to work with Vinen. He has been professor at Newcastle University since 1997. For his work on quantum fluids and quantum vortices. He has been elected Fellow of the American Physical Society in 2009 and Fellow of the Institute of Physics in 2002. He has been a member of the EP-SRC College since 2006 and a member of the editorial board of the Journal of Low Temperature Physics. So it's a pleasure to introduce and to have here Carlo Barenghi. Carlo, I stop sharing my screen. Please go ahead and share yours. Thanks again.
Thank you, Francesco. Thank you for inviting me. Let me find my screen. I hope you can see it well and you can hear me.
Yes.
So today I would like to tell you something about turbulence at very, very low temperatures near absolute zero. So first of all, let me tell you where I'm from. I'm at Newcastle upon Tyne in northern England at the borders of the Roman Empire, Scotland. So Newcastle upon Tyne, it's called because of the River Tyne, which you see in the image. And Newcastle means the Newcastle, which the Normans built in 1080. They invaded Britain, as you know, in 1066. The Battle of Hastings took them 14 years to move north and conquer the entire country. So here in Newcastle, there is a group of people working on various problems on superfluids and quantum fluids. And I would like to name some people in particular, like Luca Galantucci, M. Rickenson, Holly Middleton, George Stagg, who are PhD students and postdocs recently, and also colleagues, Yuri Sergeyev, Andrew Bagley, Nick Parker. I learned many things from them. And people at other institutions like Giorgio Krustulovic in France, and Ladik Skrbek in Prague, Ferrari in Trento, and Bagnato in Brazil. Again, I've been privileged to work with them recently. I learned many things from these people, and also EPSSC for the money. So my aim is to give you some information, some basics about this turbulence near absolute zero, quantum turbulence. And I would like you to, at the end of the day, to remember why perhaps it is interesting and what's the difference between this quantum turbulence and ordinary turbulence, which you're expert of. So I'm going to tell you about superfluid helium, about Bose-Einstein condensation and quantum vortices and the turbulence of these vortices. So let me start from helium. Helium, as you know, is a gas at room temperature. It is used mainly for making party balloons, like you see here. They also inspired some nice songs years ago. So it's not really, does not seem very scientific, but actually there is much physics behind liquid helium and a large number of Nobel Prizes associated with various discoveries in the race towards absolute zero. Helium is a gas, I said. If you cool it, eventually you get a liquid, but you need to go down to 4 degrees Kelvin above absolute zero, which is minus 273. So you get a very cold liquid, which you see in the photo. It's transparent, it looks like water. Now, when the temperature drops below about 2 Kelvin, however, it behaves in a strange way. And to illustrate this, I have 2 images here. So what you see is the liquid helium inside a glass container. So it's a closed container, and there is a pump which is pumping out the vapor above the liquid, cooling it. And you see at the left that above this critical temperature Tc, there is much boiling and bubbling. It's very violent, actually, if you see it. But when you cross the critical temperature, you'll notice that suddenly the liquid stops, becomes like a frozen lake. The bubbling stops. And that was a signal to the early physicists who were working on this strange liquid that there is something strange happening. So effectively, liquid helium becomes some kind of perfect heat conductor. Indeed, engineers nowadays use it to cool superconducting magnets, for example, in particle accelerators like CERN, very big magnets, or in hospitals for scanners. But there are also other features which are strange. For example, something which tends to drive the experimentalists really to despair is something called super leaks. Super leaks are tiny, tiny holes which are so small that no liquid would go through. The helium would not go through above this critical temperature, but below the critical temperature it can. And if it goes through, essentially the container leaks, the experiment is over and everything breaks. And one has to warm up the apparatus and fix the problem. And typically at room temperature, it's very difficult to spot a super leak with this mass spectrometer. So it gets hard, and then you have to cool down again. So, days are wasted this way. And you will see that super leaks are associated to the physics of which I'm going to describe. Now, behind everything, there is actually quantum mechanics. And you start seeing that quantum mechanics is playing a role, because if you keep cooling your liquid helium, pumping more on the vapor above the liquid, it will never become solid. To make it solid, you need to apply a very, very high pressure, 25 bars. And this is a consequence of the very large quantum mechanical zero-point energy, much larger than the binding energy of the atoms in the solid phase. So this is the first signature that somehow quantum mechanics is taking over your liquid, even if it is actually a very large macroscopic object. Okay, so then history continues, and I just want to give you snippets of this history. In 1938, physicist Kapitsa discovered that in some experiments, liquid helium behaves as if it had zero viscosity, really zero. And so this property was named superfluidity in analogy to superconductivity, which was discovered, by the way, by the same person, Kamerlingh Onnes in Leiden, the Netherlands, who produced the first sample of liquid helium. So superfluidity means the ability to flow without friction, in the same way as superconductivity is the ability for an electrical current to flow without electrical resistance. Actually, in the same year, in the same journal, Nature, in the same issue, there was also an article by Fritz London who suggested that the strange behavior of liquid helium arises because of something which two people, Bose and Einstein, had predicted in 1924. And this is really the key physics I want to convey to you in simple terms. So we must look at this Bose-Einstein condensation. I'm sure that you will remember from quantum mechanics that matter has wave property. For example, if you have a particle, an atom of mass m and velocity v, it has a de Broglie wavelength lambda, which is Planck's constant divided by the momentum mv. You will also remember from statistical mechanics that if you have a gas of atoms, which is in equilibrium, somehow the average thermal energy is proportional to kT, where k is Boltzmann constant. So if you put these two information together, you find that the de Broglie wavelength scales like 1 divided by the square root of the temperature. And that immediately raises the question, what happens if I lower the temperature and I go towards 0? Now, this question is particularly crucial if you are handling bosons, particles with integer spin rather than fermions, particles with half-integer spins, because the bosons are not prevented by Pauli's principle from occupying the same state. And in this cartoon, I've sketched energy levels, and you see at the right, you see fermions, which they are not very social. They're like under lockdown conditions, they stack up on different energy levels, whereas the bosons, risk in the presence of COVID, they occupy the same ground state close to each other. Close, I mean, in momentum state. So let's consider then what happens if you have a gas in a box consisting of many atoms at some temperature. So at high temperature, the gas consists of atoms which collide randomly, and say that the average distance between the atoms is the quantity d. Compare d to the de Broglie wavelength. As the temperature decreases, so if you look at these pictures, if I go from left to right, you will notice that the de Broglie wavelength of each atom will start getting larger. So at some point, it will be noticeable and will become of the order of the typical distance between the atoms. So essentially, we have waves which start overlapping. And at the point when they overlap, and there is the formation of really what is a single macroscopic wave, then you have Bose-Einstein condensation. Now, this is the scenario which was conceived by Bose and Einstein in 1924. I must stress that that was only realized in these conditions in 1995 by Vinen, Cornell, and Ketley using atomic condensates. So liquid helium is slightly more tricky, and I'm not going to go into the details. And the reason is that it is not actually a very dilute gas, weakly interacting gas, but it is actually a strongly interacting liquid. Nevertheless, that is the essence of the physics, which produces all the strange properties which I'm going to describe. So keep in mind this Bose-Einstein condensation, and also the fact that it takes place at some critical temperature, which is pretty low. And if you lower the system further, then there will be more and more atoms of the system being part of this large-scale macroscopic wave function, essentially the fraction of the condensate or the superfluid in the first approximation becomes almost 100% until it is 100% at 0 temperature, but the curve grows rapidly. Now, superleaks is a manifestation of superfluidity, the ability to flow in narrow slits or channels without losing energy. This is actually a consequence of the particular shape of the dispersion relation of the elementary excitations, the relation between the energy and the momentum. So here, I want to show you some experimental pictures. You see like the pressure drop measured in tiny channels as a function of the velocity. You see that it is 0 at the left until you reach a critical velocity, and then some pressure drop signifying the onset of friction becomes present. In the figure in the middle, what is plotted is the drag force. Again, the drag force on a small object, which is 0 until you reach a critical velocity. So it was understood in the 40s because of the work of Lev Landau that this happens because of the, as I said, the spatial shape of the dispersion relations. So essentially, if you have in the most idealized situation a particle, a foreign body which moves in your liquid helium or the condensate, it cannot lose energy until it moves fast enough. So when it moves fast enough, this particle sketched here, having velocity v1, then can actually produce an excitation which has momentum h bar k, where k is the wave number, and recoil in the other direction, conserving momentum and energy. But if it does not move fast enough, the particle perceives the background liquid as a vacuum, so it cannot lose energy. So therefore, we have superfluidity. But the key feature of this kind of system, liquid helium and other condensates, is not superfluidity, is the existence of the wave function, the existence and its uniqueness. So we have a macroscopic quantum wave function, which is a complex field with a real part and an imaginary part, that is to say, an amplitude and a phase, as written here at the top. Now, using some very basic rules of quantum mechanics, we can define a density, number of atoms per unit volume, using the square of the magnitude of this wave function and associate a velocity field to the gradients of the phase. Now, here there is a strange property. Because of this, you would conclude that the curl of the velocity is equal to 0. The curl of the gradient is always equal to 0. But you have to be careful. So let's measure, for example, the circulation integral around the closed path inside our system. So we will find 0 because we're integrating a field which has no curl. However, there is a possibility, which is a typical exam question for students. The question is essentially, when does Stokes' theorem apply? Well, it can apply only if the topology of the region actually is simply connected. If it is multiply connected, you can't use Stokes' theorem. So imagine that your condensate has a phase defect. That is to say, a point or a line in three-dimensional space or a region where psi is equal to 0. So there the density is not defined. The phase is not defined because it's we would have the arctangent of 0 divided by 0. And under such a situation, when you compute the circulation, you find that it is not 0. It is actually Planck's constant divided by the mass of one atom, or the whatever boson is relevant. So we call this quantity Planck's constant divided by m, kappa, the quantum of circulation. Now, in theory, we could have situations with multiple circulations. It turns out we should not be worried about that, because systems with multiple circulation, 2 quanta, 3 quanta, 4 quanta, are unstable energetically and they will decay. So what we have actually is a vortex. It is nothing but a hole, the phase defect, a line in three-dimensional space around which we have this finite circulation. The phase changes by 2 pi, and on the axis of this hole, we have that the density is equal to 0. Essentially, we have like a thin tube of depleted density, and its profile is sketched on the left. So the density is 1 in the bulk, in whatever units, and then it goes to 0. So both the real part and imaginary part of the wave function go to 0. However, around this hole, there is this phase changing by 2 pi. And that also implies that velocity field around this vortex can only be of the form kappa divided by 2 pi r. So that's the elementary textbook velocity field, which you find in the books of fluid dynamics. And here we have it, and it's forbidden to have anything else. So this is a quantum vortex. So let's compare this to classical vortices. Well, first of all, we have a fluid without viscosity. And secondly, remember that in ordinary fluids, vorticity is a continuous field with arbitrary circulation and shapes. A quantum vortex, however, is some kind of delta function vorticity with a fixed circulation and a fixed velocity field around it, and being superfluid, the flow around this defect will never stop. So this is the system, the elementary quantum vortex, which we consider. And you may ask, where do I meet this quantum vortex? Well, there are many systems, all the quantum fluids which we know, and there are many. There is not only superfluid helium-4, there is also superfluid helium-3, which is a rare isotope, actually having only 3 nucleons. It is actually a fermion, but 2 fermions can couple in a Cooper pair, like in a superconductor, and then we can get Bose-Einstein condensation and the superfluid. we have also atomic Bose-Einstein condensates, which are tiny clouds, very dilute gases. So here is a sample of some elements which have been turned into condensates, from rubidium and sodium to hydrogen and cesium, etc. There are many. Then we can, for example, we have polaritons, which are essentially photons coupled with electrons and holes. So they acquire mass by this coupling in two-dimensional systems. We can have two-component condensates of various kinds. We can have spinor condensates. We can have quantum ferrofluids. Even the interior of neutron stars is thought to be a quantum fluid. And there are even people who consider models, they make models of the early universe using axions, and they have to do with the quantum fluid. So how do we make a quantum fluid turbulent? Well, actually, it's not difficult. You just need to shake it a bit in the same way as you can shake an ordinary fluid and make it turbulent. You can apply a heat flux. You can shake it with a propeller which spins, or moving grids or forks, vibrating forks and vibrating wires. Pull rapidly a grid through the system, inject vortex rings, bombard the system with ultrasound. That works in helium. And what about the atomic condensates, which are, as I said, tiny clouds of atoms in optical magnetic traps? You can use actually laser stirring. So here there is an example. It's an experiment. This was a paper. It's done in Paris. So we have a cloud which has been flattened in two-dimensional form. The condensate is the red spot, and the blue cones represent essentially a spoon of, which is produced by using a laser beam, which is rotated within the condensate and acts as a stirrer, like stirring a cup of coffee. And at the left, you see a tiny paddle, this kind of fine mesh, which you see, which is used in Lancaster to produce turbulence in liquid helium-3, the fermionic superfluid. So the size here is millimeter to centimeter for the entire experimental cell, whereas for the atomic condensates we're talking about 1,000 microns. But you can have also much bigger superfluids. So this machine called Shrek is in Grenoble. If you look at the picture on the left, you see the scale compared to a human being. So what is inside? Well, there is some kind of double system of propellers, two counter-rotating propellers inside the cylindrical cavity. The size is about 1 meter, and they produce some kind of turbulent von Karman flow, like the Kardashev dynamo. So the question is, how does this turbulent look like? Well, since I tend to do theory and simulations, let me start by numerical visualization. So that is the way I perceive these turbulent systems. So what you see at the left-hand side is quantum turbulence in an atomic Bose-Einstein condensate. And here, this kind of blue wobbly sphere is the cloud of atoms, the surface of the density at some threshold level. It's wobbly because within there are these vortices, which are the purple lines. This is a snapshot. So you see a dozen or so vortices which interact within the blue cloud. They reconnect, they move each other, and essentially some kind of tiny drop of superfluid. That's how you can think of that. At the right-hand side, there is a numerical simulation of turbulence in liquid helium. So here we're mimicking something on the scale of the millimeter to centimeter. We have many, many vortex lines. You see the axis of the lines. Like in the picture at the left, you do not see the velocity field. You only see the axis of the vortices, and you are not given information whether the vortices rotate clockwise or anti-clockwise. But you can imagine from the tangleness of this picture that the flow is rather complicated looking. Now, this is my view of the systems, but people doing experiments actually can visualize vortex lines individually. And for example, a nice technique is this one. At the right-hand side, you see a photograph of two vortex lines which are reconnecting. So they're actually colliding, and as they collide, they recombine, changing the topology. What you see is a string of dots. The dots are actually tiny tracer particles. They're made of solid hydrogen. So you sprinkle some hydrogen, which become immediately frozen within liquid helium, and forms a tiny micron-sized snowball, which becomes trapped within the vortices. So the picture at the left shows the vortex in red, and the blue spheres are the tracers. Notice the size. The vortex core, this tiny tubular region around which the circulation is fixed by the quantum of circulation, is very, very tiny. As I said, it's less than a nanometer, and the size of the tracers is a micron. So rather than trapping, it's like we should say that actually the vortex line is interrupted by the presence of these tracers, which are energetically stable there. They like to be trapped. And there are many other things which experimentalists can do to measure the turbulence. For example, they can measure the total length of vortex lines using various methods. And in atomic BC, they can also see individual vortex lines, and they also take direct images of the expanded condensate. They have to expand it a bit before to take them to a size of about, say, I would say 100 microns or so to take an image. So turbulence systems have been created, and what is interesting is that over the last few years, two somehow limiting cases of turbulence have been identified. So people interested in this kind of problem look for classifications to start with, and there seems to be two regimes, and the names which have been given are the following: Kolmogorov turbulence, after the famous Andrei Kolmogorov, of course, of ordinary turbulence, and Vinen turbulence, named after Joe Vinen, who is a great pioneer of liquid helium. So let me describe now briefly what are the physical properties of these two regimes, and keep in mind that the information which I'm passing to you is rather recent in a sense. I think it's strong enough to be discussed in various papers, but we're still learning about these systems. So what is Kolmogorov turbulence? It's typically the turbulence which you observe in liquid helium when it is agitated, when it is stirred by a machine like the Schreck experiment, the von Karman propellers. So we have forcing at the large length scales, and the turbulence which is observed seems to be very similar, really, to the ordinary homogeneous isotropic turbulence which you can produce in a wind tunnel. In fact, people built also superfluid wind tunnels, I must add. So what do we see in these systems? We see the signature of the Richardson energy cascade. So energy which is input at large length scales seems to be transferred with very little losses to smaller length scales, to larger wave numbers, and there is a noticeable power law, which is the K minus 5/3 energy spectrum. Another signature of this turbulence in these systems is the decay time, which we can predict for quantized vortices in this regime to vary like T to the power -3 divided by 2. Then there is the second form of turbulence called, as I said, Vinen turbulence, which looks like a random flow. So we don't see signs of the energy cascade of the inertial range. It looks like a random flow with a correlation function of the velocity which decays very rapidly, and the decay time, the decaying behavior is quite different. Now, to illustrate the Kolmogorov regime, think of this simple experiment which has been performed actually in the laboratory and also being performed numerically. So imagine you have your system, some kind of large box, and you keep injecting vortex rings. It's easy actually experimentally to produce vortex rings and inject them in a sample of liquid helium. So we inject vortex ring, essentially we inject energy at some known rate, and the system of the turbulence will build up because the rings will collide, reconnect, interact, and create this random looking tangled mass of vortices, which you see in these figures. So the typical distance between these vortex lines, these quantum vortices, will decrease as the total length will increase. And the corresponding wave number, k delta, where delta is the typical spacing between the vortex lines, will actually become larger. So you create in this way some inertial range, and over length scales between the injection wave number and this kd associated to the average distance between the vortices, you will notice properties such as the Kolmogorov energy spectrum scaling like k to the minus 5/3, or other properties of the turbulence like the fact that the velocity statistics are Gaussian. I mean, the velocity is not the velocity differences. However, at much larger length scales, larger than the typical value k delta related to the vortex separation, the Kolmogorov scaling does not appear any longer. There is another scaling, k to minus 1, but that is actually easy to recognize because that scaling is actually the energy spectrum of a single vortex line. So if you look at very, very small length scales, what you see is essentially the vortex, which is the closest to you, and so you see a k minus 1 scaling. And that is consistent with the evidence which we have. So here is an example of some calculation with a spectrum of these kinds. The Kolmogorov minus 5/3 regime at the left, and then at the expected wave number, the spectrum of the energy turns to the k minus 1 power. And I stress that this is not one of the best pictures of this energy spectrum. It is there are better examples. So from this picture, you could only say, well, okay, the energy spectrum is consistent with minus 5/3, but it's not exactly the same. In the experiments, however, as I said, experimentalists can get much better spectra, and also in the numerics, one can get better pictures than this. So let's try to think why there should be a Kolmogorov energy spectrum in a system of quantum vortices. So here there is a figure of these tangle of vortex lines at a fixed time, a snapshot, and they've been actually color-coded in the following way. So what we noticed is that in this regime in this Kolmogorov regime, the vortices tend to create some kind of bundles, in the sense that there is a partial polarization of the vortex lines, which on the average makes some kind of bundles. Now, why the bundles are crucial? The cartoon at the right-hand side explains in a simplified one-dimensional fashion. Imagine you have these 4 arrows, red arrows, representing 4 oriented quantum vortices aligned in the same direction. So clearly, if you compute the circulation around them, it's large, it's 4 quanta, and on the average, there is a large-scale flow which is created, which actually contains much kinetic energy. But if your vortices, if the arrows are oriented one up, the next down, then there is no average flow velocity, which is actually corresponds to this configuration. So the vortex configuration contains very little energy in comparison. Now, the figure at the left-hand side colors the vortex line according to somehow the average vorticity obtained by integrating the vortex lines in some suitable way, essentially measuring the presence, detecting the presence of bundles. So when you see a yellow line, it means that it's part of a polarized bundle. And when you see a red line, it means that somehow it's actually in a region where the vortex lines are random to each other. They are unpolarized. So it turns out that most of the vortex length is unpolarized, it's random. But there is always a fraction of polarization and of yellow lines, and they actually are responsible for the Kolmogorov energy spectrum. So the yellow lines alone would produce the Kolmogorov spectrum, and actually the entire system produces the Kolmogorov spectrum. It's only the red lines, the unpolarized random lines, which produce the expected K-1 spectrum. So in other words, this partial polarization produces the natural range. And the idea, I think, the explanation which I can come up with is that although a single quantum vortex cannot undergo the classical vortex stretching because of the constraint of the quantization, if you have a bundle, the stretching can take place because you can squeeze a bundle of vortices more or less and create smaller structures. So somehow, this partial polarization makes the vortices to behave like classical eddies. In the second regime, the Vinen regime, this does not happen. You keep forcing your system, but actually you do it at a smaller rate. And the wave number corresponding to the intervortex spacing does not develop, moving to the right. And you end up with the spectra which look like these two. There are two realizations. You see that, first of all, there is not much energy at the large length scales in this periodic computational box. There is quite a lack of energy at the large length scale. Perhaps in these pictures, a couple of orders, a couple of decades of energy are missing. Then you notice that the energy peaks somehow at intermediate wave numbers rather than at the left, and that really the scaling law for large wave numbers is always K-1. So this is the signature of random vortices. So it's quite noticeable, the -1 spectrum, the red dashed line shows you the slope of the -5/3 spectrum, which is much steeper on this scale. So you may ask, oh, well, is this Vinen turbulence an oddity seen only once? No, now we can say that it has been seen in many systems. So I start from experiments done using very different techniques in helium-4 and helium-3. So in helium-4 at temperatures of the order of the Kelvin, in helium-3 at the temperatures of the order of the millikelvin. They are very different quantum fluids. And in both, the Vinen and the Kolmogorov regimes have been differentiated. There are also numerical simulations. For example, simulations of tangles of vortices driven by heat flux, provided the heat flux is small, which we've done in Newcastle. Simulations of the actual phase transition, the superfluid phase transition, the onset of Bose-Einstein condensation at the critical temperature produces actually a transient state of turbulence, which is Vinen-like. In atomic condensates, which are, as I said, and you've seen in the picture, they are small systems, you cannot really distinguish there is not a large scale separation, and the turbulence which has been produced when measured has always been Vinen-like, although in some numerical simulations, the transition to Kolmogorov has been seen. And even simulations of dark matter in the early universe, strangely enough, actually produced in their own quantum vortices a kind of turbulence which is actually Vinen-like rather than Kolmogorov-like. So here I want to show you two pictures of numerically computed turbulence, just to show you that this is the difference between Vinen and Kolmogorov cannot really be seen with the naked eye without doing some numerical analysis. Essentially, in this cubic box with periodic boundary conditions, at the left we have a Vinen regime, at the right a Kolmogorov regime, and the vortex length, which somehow measures the intensity of the turbulence, is the same. However, they are different, and the difference has been color-coded in this particular picture in terms of the locality of the velocity field. What do I mean? We know that the vortex line, at the given point along a vortex line, the motion of the vortex depends on two things. Depends on the local curvature. If a vortex is straight, it does not move. If a vortex is slightly bent, it will actually move in the binormal direction with speed, which is proportional to the quantum of circulation and inversely proportional to the local radius of curvature. So there is a local effect which moves the vortex lines in the binormal direction. But also we know that the vortex line is moved by the other lines. That is what I mean by non-locality. It's not the local curvature which determines the velocity, the direction of the motion and its intensity. It's the fact of the other lines, the velocity field of the other lines. That is exactly what is measured by this color coding. So small values are green and blue, and the large values are the yellow-red. So you see that in the Vinen regime, which is more random-like, as I said, although we have the same amount of vortex length of quantum vortices, the motion is random, so the vortices don't feel the effect of the neighbors because essentially the neighbors are random and they tend to cancel out. On the right-hand side, you see the Kolmogorov regime, and perhaps you can, by looking, knowing the answer, actually you sort of see the presence of bundles, of these polarized bundles, and the non-locality is actually much more, much stronger. The lines are more red in color. But this is not the end of this story, which I wanted to tell you, because particularly low temperature, there is very little thermal damping. There are very little thermal excitations. And there is another effect, which seems to be peculiar of quantum vortices. So a vortex line, you should know, can sustain waves, which are some kind of helical displacements of the vortex away from its straight configuration. So this is very well known. In fact, they're called Kelvin waves because in 1880, Lord Kelvin actually thought of them and derived indeed the correct dispersion relation for these waves. And in the picture here at the left, you see a vortex line in red, which is very wiggly. So it has actually many Kelvin waves of various wave numbers and amplitude. Now, it was actually a great idea of Boris Fistonov in 1995, who realized that when these waves have large enough amplitude, they interact. And this nonlinear interaction of the Kelvin waves produces shorter waves, which then produce, therefore, by interaction, even shorter waves. So we have actually the possibility of a Kelvin wave cascade taking place on individual vortex lines. Now, this Kelvin wave cascade can therefore shift the energy which the Kolmogorov cascade has actually brought from the very large length scales of the forcing, which is macroscopic, to the very short length scales of the typical intervortex separation. So energy flux can proceed further downscale to larger and larger wave numbers. We have a superfluid, there is no damping, so nothing actually stops the vortices from becoming more and more wiggly. At some point, however, some extra physics will kick in, because when the wavelength of these Kelvin waves becomes short enough, then the vortice will start radiating sound. Essentially, sound means phonons, which means heat. And the picture at the right-hand side, for example, shows you the sound pattern, these spirals, the density in the form of spirals wave produced by these two tiny dots at the center, which are actually two parallel vortex lines, which are rapidly rotating around each other. So at that point, energy is lost, as I said, and becomes phonons. So we have the possibility that the energy shifted to small scales by the Kolmogorov cascade can be shifted even to very microscopic length scale by the Kelvin wave cascade. In fact, this theory has been worked out, and the best which we know at the moment is the theory of Lvov and Nazarenko. They used wave turbulence theory to describe this one-dimensional Kelvin wave cascade, and they predicted the spectrum for the occupation number n, and also from there we get the energy spectrum, which it turns out is still the power minus 5/3. And when they did it, I thought it would be impossible actually to see that in the numerical simulations, but actually progress in computing has been fast. So I want to show you this picture of a calculation done in 2017, where actually the range of wave numbers covers 3 orders of magnitude from 1 to 1000, you see. And you see the spectrum of the energy. At the left, you see the Kolmogorov energy spectrum, the classical one, due to these polarized bundles, K minus 5/3 due to the bundles, until you find the end of the spectrum at the typical wave number corresponding to the individual vortices, which is actually 80 in this case. And you see that the slope stops, the downward slope stops, and there is some kind of bottleneck. There is like a plateau. And then there is actually a continuation with the second cascade, which is the Kelvin wave cascade, exactly as predicted. The bottleneck was also predicted by Lvov and Nazarenko. So essentially that represents the impedance which the system actually, the system tries to prevent the energy from coming down from three-dimensional eddies into one-dimensional vortices. There is, as I said, there is an impedance matching problem, and that clearly is causing the bottleneck. So this is actually the scenarios which I wanted to describe, but there is something else which I would like to point out before finishing, because I told you the little which we have learned about the dynamics, these regimes of cascades, and from the dynamics, I would like to move to the topology. And why is that? Well, because this is really unexplored territory. In 2013, William Irvine and his student Kleckner at the University of Chicago succeeded in creating something which actually many people tried before. They succeeded in creating a vortex which is knotted. And they did that in water using some kind of clever drive using three-dimensional airfoils. So what you see in this image is actually a very thin vortex with a very thin core in water, visualized by tiny bubbles. And believe it or not, actually, it's very well described in the paper, this is actually a three-dimensional vortex knot. It's a trifoil knot. So that was a very nice result. As I said, many people had tried without success. And immediately the question is raised, oh, well, so if you can make a knot, does nature make knot? So is turbulence knotted? Is classical turbulence knotted? Now that question seems difficult to answer because ordinary turbulence is the turbulence of a continuous vorticity field. So how do we actually tell whether it is knotted? It's not simple. But what about quantum turbulence? Well, here we have discrete individual vortices, and they're clearly knotted. So if you look at this picture, you see actually a computed turbulent configuration in a small system. This is actually a snapshot of a tangle which is sustained in a statistical steady state of turbulence. There is driving, there is dissipation, it's open, so all the vortex loops are closed. The vortices keep interacting and reconnecting. So the number of loops keeps changing, but the properties of the turbulence have achieved a statistical steady state. Now, if you look at this picture, which has been colored in a particular way, you cannot but think that there are knots. Now, the coloring is actually done by marking each individual vortex loop with a different color, and actually making these lines actually like tubes, much thicker than what they would be in reality. In reality, the thickness of these vortex lines, I remind you, is microscopic. It's the size of an atom, really. So it would be like 1/10,000 of the distance between the typical distance between the vortices. So not the thin tubes which you see here. Nevertheless, here you see interesting things. You see Kelvin waves, those helical shapes. You see some very long filaments, and you see something which makes you to be suspicious of knots. So the question is, how do we make sure that we have knots? Well, we have found numerically, for example, that systems like this, or even bigger, with more vortices, contain many links. What are links? I mean, Hopf links, like two circles, which are actually configured in this way. So they are linked together, only a reconnection can undo them. So how do we measure the knottiness? So we came up with this idea. So we can actually do the following. Like in knot theory, knots are classified. There is a way of associating polynomials to to curves which are knotted. Actually, there are many polynomials, and here I concentrate on the Alexander polynomial. So you see that in the figure, a number of knots, a standard knot table, like produced by Tate, the friend of Lord Kelvin, who actually studied knots for the first time, motivated by Kelvin, who thought that knots perhaps were actually his way to understand the fundamental properties of matter. He thought of knots as atoms. So you see, like at the top left, you see like a circle, which has a trivial topology. It is the unknot. It is not knotted. And then you see the trefoil in red. And then the third knot is the figure 8 knot, and so on, more and more complicated knots. So each of these has actually polynomial. For example, the unknot has the degree nu equals 0, and the trefoil has the degree 2, the way it's done here, and so on. So the more complicated the knot, the higher the degree. And this can be computed numerically. We can actually find an algorithm to decompose our turbulence, which consists of loops which may be knotted, and go and find out one by one whether they're knotted or not. And what is the result? So what you see here is turbulence in a statistical steady state. So time is marked at the bottom, and what is plotted is actually the largest degree of Alexander polynomial found in the vortex configuration as time goes on in this statistical steady state. The blue curve is actually the second largest knot which you find. So you see that actually the knottiness defined this way fluctuates widely because reconnections keep doing and undoing the knottiness defined this way, but still remains quite large. So we have knots which typically fluctuates around a degree which is about 30 or 40 in this particular case, the most complicated knot, and the second most complex knot has a degree of at least 10. So they are really difficult knots, which is very difficult it would be impossible actually to recognize with the naked eye without doing a calculation. So most definitely this turbulence is full of knots. Indeed, we can also work out a probability of finding knots given a long enough computation. Essentially, in the statistical steady state, we keep measuring and produce statistics. So what you see here is nothing but a knot spectrum. You see that there is a high probability of finding, therefore, loops which are not knotted, but there is a power law. It turns out to be very close to -3 divided by 2. So there are very frequent, it's not Gaussian, it's a power law. That means the tails are high. So in fact, in any system like this one, which I showed you, in any snapshot, there is really almost certain there is some gigantic monster knot in the configuration. So they typically are very long loops, which may break up quickly, but then they will reform. And this kind of result actually is very similar to what people are finding nowadays when they study the knottiness of polymers or long molecules like DNA. So vortices are not behaving very differently. So what makes the knots, what destroys them? It is reconnections. That's the last thing I want to say today. Having discrete individual vorticity, individual vortex lines means that we can actually study the way the reconnections take place. Reconnections are dramatic singular events which cost energy because sound is radiated away at each reconnection event. So schematically, can be represented like this. Imagine you have two vortex lines, one red, one blue. They come close to each other at some distance delta. Eventually they collide, so the distance is 0, and then they reform, but they exchange the heads and the tails. So there is a line which is half red, half blue, and the other line is half blue, half red, moving away. So we found that this distance, the minimum distance between the lines, seems to obey some universal scaling laws. We have done lots of numerical simulations using various models of quantum turbulence, and we keep finding these laws, which we can also derive using standard dimensional analysis. So there are two regimes, essentially. One in which the minimum distance scales like the square root of time, and one in which is scaled linearly with time. So the first regime essentially describes two different phenomena. One is when the lines are very close to each other. Remember that the vortex lines are essentially tubular regions of depleted density. And you can think of them as well described by an equation like the Gross-Pitesky nonlinear cubic Schrodinger equation. So when they're very, very close to each other, the vortices actually, they deplete the nonlinearity. The psi cube term in the nonlinear Schrodinger equation becomes smaller because the density goes to zero near the two axes which are merging. So from the linear Schrodinger equation, you can easily recover this square root law, and that was done by Nazarenko and his student West some years ago. However, this regime is also true in general when you have vortex reconnections in turbulence of the kind like in the schematic diagram above. So the two vortices interact via the mutual velocity field. So one vortex moves the other, and that gives this scaling. But there is another scaling, which is actually typical of configuration, where actually there is one vortex which is driven by its own curvature, or in a system like an atomic Bose-Einstein condensate, density gradients. So that's the most typical situation in atomic BECs studied in the lab. So we have two different regimes. Now it is interesting, this result is new because it was obtained only a couple of years ago. And last year, Hussain and his collaborator Yao actually wrote a couple of papers in JFM, and they computed the connecting solutions of the Navier-Stokes equation, trying to make the vortices as thin as possible, and they recovered both scaling laws in these two papers. Right, and at this point, I think I'm running out of time. I think I've told you the story, what is there. I hope there is something there interesting to you, some ideas to pick up, or perhaps those of you who work on ordinary turbulence perhaps can contribute and actually give us some ideas. And I would be particularly curious to know about analogies to Vinen turbulence or analogies to the knottiness problem I described. Here I want to finish with a couple of review papers. If you want to know more about these systems, there are these two review papers available. I've been actually privileged to work with these people here, put together results. So the first is mainly dedicated to liquid helium, and the second to Bose-Einstein condensates. And at this point, I'll stop and thank you.
So thank you, Carlo, very much for this presentation. The stage is open for questions. If there is someone who wants to ask, just unmute your mic and feel free to ask a question.
Hi, this is Jim Brasseur. I asked a question in the chat, so I'll just read it. Since you, at the beginning of your talk, you pointed out that the quantized vortices are attached to places where the wave function passes through zero. So the question then is, how does one interpret? I'm not a quantum physicist, so how does one interpret psi equal to zero? And since psi squared is the number density, what does that imply about what does number density mean? Number density of what? What is that?
It's the number of atoms per unit volume. So it means simply there are no atoms there, and you can make actually such a vortex line artificially by having a tiny wire in your system. So you have like a cylindrical cell. There is a very thin wire, a metal wire, and somehow you manage actually to create a circulation around the wire. So you would have quantization. So you would have a phase which changes by 2 pi around this wire. There is actually flow of atoms driven by this increasing phase profile. It keeps increasing, going around 2 pi each time. And on the axis, there are no atoms because there is the wire. So this is artificially produced, and you can make the wire bigger if you have like a cylinder. So you would have circulation and you have a quantum vortex. However, nature can actually spontaneously create such a situation, creating this defects line within the fluid without us doing that. A typical example is actually a phase transition. If you take a system which actually is cooling, going through the phase transition, the phase is actually absolutely random everywhere because the system has to organize itself. So it goes from a classical regime where there is no wave function down to a regime where there is a wave function and there is a phase. So the phase is born and it's random everywhere. It's a bit like when you make, it's a bit the same when you actually make a crystal, yeah? So you will have a random phase, essentially lots of, we call them ghost vortices, which organize and they become long vortices, real vortices, these defects, and they would be therefore a transient state. So nature actually creates these three-dimensional defects. They are lines in three-dimensional space which represent zero density on the axis.
Carlo.
Oh, hello, Srini.
How are you?
Well, thank you.
I'm wondering if you could say a little bit about the importance of knottedness for, say, dynamics or anything you can think of.
I do not know. I've been asking myself, is this interesting? Is it important or not? Now, there is something which one could say very naively. First of all, if you create knots, essentially you're storing some energy in the system because it takes energy to make a reconnection. So somehow, if you have a knotted kind of turbulence, the knottiness packs the energy. So there is this energetic feature. And the second feature is that perhaps there are rules about the knottiness actually evolves dynamically. There is a paper by Irvine and Kaufman, who is Louis Kaufman, a great knot theorist in Chicago, and they actually argued and they actually provide some numerical evidence that if you make, if you have like a large scale, a large knot, a knot of high order, if you make it to decay, it tends to do it along some particular topological pathways, not others. So you go from essentially, it's a bit like radioactive decay. There are some selections, there is a selection of paths. So perhaps that's another way of looking, give us a handle for looking at the decay of turbulence. Really, I do not know what it means. At the moment, I'm just interested in this feature. I think that whatever it is actually a curiosity-driven problem. And the first thing to do is to be able to quantify it. Because if we cannot quantify the knottiness, we cannot proceed in any rational way. And
I have no problem with that.
Yep.
I wonder if reconnection sort of cancels out these knots very significantly. So I was surprised to see this high degree of knottedness in the simulations.
Well, reconnections also create knots.
Yes, indeed. Yeah, sure.
So there is a balance in the long statistical study. I can show you actually what I mean by this if I share the screen again. I think if I look at this here, so, right. So this is a paper actually where you see some spectrum which is consistent with Kolmogorov, -5/3 and -1. And this is the system producing such a spectrum. So it's some small vortex tangle. And this is actually the evolution of the vortex length. So the system is created, driven to a long statistical steady state. So when we measure this knottiness, we actually look at the statistical properties. So clearly, the knottiness forms, but when we are in these regimes, the knots keep being created. They're destroyed, but also they keep being created. And what is interesting is that there is a high probability, there is actually a relation between length and knottiness. That makes sense because it is the same for DNA and for long molecules. You know, the longer they are, the increase the probability that they are knotted. And there is some kind of regimes, equilibration, which is reached. So it's somehow a property of turbulence. But what it means actually dynamically, I'm not sure. I'm very curious. It would be nice to do it for Navier-Stokes. The problem which I see, actually, once I tried to supervise a student in a brief project, and we try to actually do the same for Navier-Stokes. The problem is that the measure of the knottiness can only be statistical, because in a numerical simulation, vortex lines may actually go from, they're not quantized. So you can have a region of intense vortex lines, and then a region of weak vorticity. And you want to be able to close a loop, because the solenoidal condition must be there. So you can only do it in statistical sense by creating perhaps a little bundle of vortex lines and see whether you can define the knottiness this fashion.
I'd like to remind you of the link between helicity and the degree of knottedness of lines to cite.
Yes, indeed. Yes, that's right. That's
and
right.
The fact helicity can be positive and negative, so it can cancel. But I saw a paper recently, which I cannot say anything about, it's math, but they talk about the fact that if there is a singularity, we know already that there has to be a singularity in the curvature of vortex lines. But I was wondering whether there would be one also in the torsion, which corresponds.
Yes, this is a notorious problem. There are ways. There is not an agreement about what is the definition of helicity for a superfluid vortex, for a quantum vortex. Some people come up to the point that it cannot be defined or it's zero. So it's conserved because it is zero and it must be zero. Some people actually find a way to define it by taking a limiting process. So then they obtain some kind of analog of helicity. And then the question is it conserved? Nobody knows.
Well, for Euler, it is conserved, right? And it's very
easy. But this system is not Euler. In fact, the most interesting feature here.
Yeah, but you make an analogy between that system and Navier-Stokes. So why can't I make one with Euler?
Well, right. The difference is this. If you have a system which is Euler, reconnections are forbidden because there is conservation of helicity. You can prove it from the equations of motion. And it does not dissipate because it is inviscid. Now, in Navier-Stokes, you lack the conservation loss of energy and helicity, and you can have your reconnections. Now, a superfluid has this property. It conserves the energy provided you keep the balance between kinetic and acoustic, and also energy in the core. So this total energy is conserved.
Yeah.
But the helicity is not necessarily defined because the classical definition runs immediately into problems. The delta function, the vorticity is a delta function. Okay, and the velocity is actually goes to infinity on the axis. Now it does it in a slightly different way because the vorticity is singular along the axis because it points along the vortex, and the velocity is actually the tangential component which diverges. So that gives you some kind of escape route, which has been used in some papers. But not everybody agrees. And in any case, nobody can prove anything about a helicity defined so far. So they can only look at numerical evidence because in the experiments, well, there are actually some experiments in Chicago where helicity was measured, but for very simple systems. So it's totally an open problem. It's quite interesting for the implications. So I have my own view on this, but it's not much relevant.
Well, it is relevant, but anyway, thank you. But then it means that when kinetic energy goes into acoustics, then the question is, what is it in the acoustics, in the phonons, whatever it is, that you could define as helicity?
That's a very good question. It's tricky because you're going to have large amplitude waves, and we don't even know how they thermalize really. So good question, but not the answer.
Interesting.
Could I not say that the existence of quantum stresses somehow eliminates the conservation of helicity?
Well, but the people who actually managed to define helicity would disagree. They would say, yeah, we can define helicity. I mean, a quantity which is somehow in analogy to classical helicity.
Yeah, I'll not monopolize any further. There may be others. Thank you.
Hello, Carlo. Can I ask a question?
Yes, please.
Earlier on in your talk, you said that at wave numbers higher than where the 5/3 is, you have a -1 spectrum, and you said that this was effectively a point vortex, giving you -1. Then later on, you say that actually it undergoes a Kelvin wave cascade in case of -5/3, and you saw some -5/3 then, which did not seem to agree. And later on, you talked about knots and reconnections, which indicate a different dissipation mechanism, even a different cascade mechanism, and perhaps which might not agree at all with the Kelvin wave cascade. So what's the story?
Well, the story is that at large, that in the Kolmogorov regime, I mean, the typical helium experiments driven by a large-scale propeller, for example, or even in Bose-Einstein condensate, if it is actually large enough, and it is stirred a large length scale, you will see actually a classical Kolmogorov cascade. At some point, you may, depending on the resolutions, depending on the regime, you may actually spot that this slope actually changes because you're seeing individual vortex lines, and then it flattens. And then this flattening, if you follow, because you have actually more numerical resolution, I stress, this is only numerical, because there is no physical evidence about the Kelvin wave. There is no experimental evidence, really, sure, about the Kelvin wave cascade. If you have more resolution, this flattening is -1, but then becomes a plateau, which lasts for a while. And then you go down into another slope, and you notice that the vortex lines are very, very wiggly, and there are these Kelvin waves which interact, and there is a flux. And so the energy keeps going down into individual ropes until actually they rotate so fast and so tiny, then they emit sound. I mean, that's the basic story.
And how, I mean, so number one, so there's a -1 between the -5/3 and the plateau.
Yeah, there is a -5/3. Then there is this kind of bottleneck plateau. We only know it from some numerics, large-scale numerics. So, and then there is the second spectrum, which you see in a big three-dimensional system, like in this calculation. You can also produce the second spectrum without the first. That is easier. In fact, the best agreement between the theory, the wave turbulence theory of essentially Zakharov, Nazarenko, and the numerics is actually when the numerics is done without attempting to capture the classical Kolmogorov cascade. So you have a system like an individual vortex, yeah, and you shake it and you see all the waves. Essentially, you limit your numerical resolution in that range. What is very difficult is to capture both, but as I showed in that picture, there are actually calculations which succeeded in capturing both. Big problem is what is actually the experimental signature of the Kelvin wave cascade. At the moment, it's very indirect. We know it from the way the turbulence decays. That is actually what leads to what led to this idea. What is the evidence of this bottleneck? Nobody knows. I thought, well, perhaps there are some kind of vortex structures at that kind of wave number regime, but there is no experiment which can actually tell anything for sure. So at the moment, it's an idea which makes sense because there is a theory and because there are some numerics and they back each other.
Another aspect of my question was whether this Kelvin wave cascade that gives the -5/3 is consistent with the knots and the reconnections.
Oh, it's consistent with the knots. I don't know. Somebody actually found that the reconnections as such can actually, if you have a system with enough reconnections, that alone could induce a -5/3 spectrum. I'm not sure actually that I think it is possibly true. I'm not sure actually how much we should conclude that reconnections drive the Kolmogorov spectrum because that will depend, then the spectrum will depend on the intensity of the turbulence, because the intensity of the turbulence, we know the scaling laws, how many reconnections there are for a given vortex line density. There is a scaling which is 5 divided by 2. So we can actually figure out how many reconnections there are. And so the amount of Kolmogorovness, I would say, would depend on how many reconnections we have, how frequent they are. So I'm not so sure about one can say that. So I think the link between knots and the spectrum, I think, is weak, perhaps, or we don't know. I think, frankly, we don't know.
Right. Thank you, Carlo. I will turn myself off.
Carlo, may I ask a question?
Yep.
Hi, this is Larek speaking. That's about dissipation in the Kelvin wave cascade. I mean, in helium-4, we all believe that, I mean, the way of energy dissipation is due to phonon emission at very high K vectors. In helium-3, this is not the case, because helium-3 has vortex cores, which are much fatter. And because of that, there are kind of bound energy states in the vortex cores that are called Carolin-Matricon states, and you may excite these states. So the question is, if we go the same direction and we go to Bose condensates, which are even fatter, these vortex cores, what do you think is the energy dissipation there?
I think it's actually sound, because the atomic Bose-Einstein condensates of the kinds, people have been doing this kind of experiment with quantum vortices, are really very dilute gas, and they are really well represented by the Gross-Pitesky nonlinear Schrödinger equation. All sorts of properties of the ground state, of excited states, linear and nonlinear, and can actually be recovered by this equation. And there are also, good generalizations of the equations of the Gross-Pitesky equation to finite temperature. So this model is very, very good. And in this model, in the Gross-Pitesky theory, the structure of the core is very simple. There is a hollow core with a single delta function on the axis. So there is a depleted tube, density going to 0, like in my sketch. That's the simplest case we can think of. So there are no there are no special, states attached to the core.
So the answer could be that because
it's phonons, so it's sound here for this system, clearly.
The answer could be that because of the complexity of helium-3 vortex cores, if this complexity wouldn't have been there, then eventually the phonon emission would happen as well. But because there is additional mechanism, maybe it comes first and it doesn't go as far as
correct. So thank you for, I think I appreciate the remark, helium-3, clearly. I just, try to describe things in general, and often I'm guilty of this. I tend to, refer to the simplest case, which is actually the weakly interacting Bose gas, or helium-4, because the evidence from experiments is much larger. It is the most studied case. I want to add, however, that there are other systems which actually worth looking from this point of view. Quantum ferrofluids. In quantum ferrofluids, actually, the spectrum of the excitation it's like the helium spectrum with rotons. So I don't know actually what are reconnections and issues of this kind in quantum ferrofluids. Soon, people will hopefully see whether there is more. And perhaps you can build other systems which perhaps mimic helium-3 also.
Also taking advantage of saying hello to Larek.
Oh, hello.
Thank you, Carlo. That was very nice.
Thank you.
Yeah. So I would like to ask if there are more questions. We had already quite an active debate. If you have any question, just unmute your mic. Feel free to ask, or you can just write on the. I think there is some participant who wants to ask.
Can I ask a brief question?
Hello.
Hello, it's Koji.
Hi.
Okay. I have a question on Alexander polynomial you used. And beside Alexander, there is another kind of polynomials, say Jones polynomials, which is a bit more powerful in the sense that Jones can distinguish a knot from its mirror image, whereas Alexander cannot. So I was wondering, if you're interested in helicity, it may make sense to go for Jones polynomials.
Well, yes, actually, when I decided to try that, I went for Alexander because it was, I managed to compute them, okay? There are also the Jones, there are other polynomials. So this exercise, which you suggest, is important. It should be tried. I doubt it changes the scenario. I think perhaps what is more urgent is actually to explore the knottiness of a number of systems. So with the same tool, compare various kinds of turbulence, various kinds of disorder states. For example, is it the same for Kolmogorov for Vinen turbulence? I don't know. Is there something similar in ordinary turbulence? I'm very curious to know if people here who know more about ordinary turbulence can tell me about the knottiness of ordinary turbulence.
Right. Thank you very much for your nice talk.
Is there someone else who wants to ask a question? I see someone who unmuted his mic, but not sure. No, this doesn't seem to be the case. So you can write in the chat if you want to ask a question. Otherwise, I think we are. Yeah. Okay. So it seems there are no other questions. So let me take the chance to thank our speaker again. Thank you, Carlo, for the very interesting talk and for the discussion which generated. And I hope to see all the participants participating in the next meeting in the next webinar of LMFL next week. So thank you, Carlo, once again, and have a good evening to all of you.
Thank you.
Thank you.
Bye.
Thank you. Bye-bye.